Okay, Assalamualaikum and a very good afternoon. Okay, so now we proceed to our next chapter, deterministic modeling. Okay, we are going to categorize this lecture into quite a number of parts because it's a little bit extensive, all right? So as a first part, we are focusing on the linear programming. Okay, maybe some of you already heard about linear programming, and maybe some of you haven't. Okay, this programming is a very important tools, okay, or methods in optimization problems. Okay, why it is important? One, because it's straightforward. Two, because it's in application part is very very crucial for us to understand this. Okay, because we are dealing with how to get the best possible results that we can achieve. Okay, in the sense of how can we get the optimized. Let's say you want to focus on output, you get the optimized output. You want to focus on the maximum value, you get it. Okay, and some of the situation, the maximum value is not actually the optimized value. Okay, meaning that if let's say you get the maximum value in your production output, it may not necessarily so, since you have other limitation or other constraint that you need to consider. Maybe the optimized values, the value for the optimized output is less than the value on your maximum output. You don't know. Okay, you don't know unless you are looking at it very constructively, and you translate your problem into mathematical formulation. Okay, so these are the example, the concept of the linear programming. Okay, so example, if let's say you have just a mathematical formulation. Okay, if let's say you have two variables, in this case your x and also your y, and then you know already you need to try to find the maximum value for your 3x plus 4y. Okay, how we get that particular constant or coefficient next to your x and also your y, we're going to address it later. Okay, to simplify things, we have this one first. Okay, we have the maximization problem here. But at the same time, we have other limitation that we need to consider. Okay, so for example, in this case, you have two constraints. Okay, that limit your ways to solve this. Okay, so the constraint, in the sense of two different limitation there. Okay, the first one, you have 5s plus 8y less than 24. And then one other things, okay, for example, your x and y must be positive values. Okay, for example, especially in a production, where let's say your x is a output. Okay, or your x is a, let's say, a thing. Okay, if let's say your company, you produce pen and also pencils, your x is pen, your y is pencils. It does not make sense, right? If your x and y is a negative value. Okay, so you imagine that is the case. That's why we have this certain limitation for us to move forward. Okay, so these are the example of how can we able to find the maximum value in this case. All right, so how to do this? Now we are talking about a feasible solution. Okay, so feasible solution means that you try to satisfy all your constraint, your available constraint. In your case right now, your constraint is just two. But linear programming, you're not limited to only two constraints. Okay, sometimes it's more than three, four, and so on. And maybe some of you may think, oh, so how are we going to solve this if you have a lot of constraint? Okay, you always have to remember we have a machine, all right? So we have a computer, and then the most important part is how can you construct your valuation on your constraint, the constraint that you need to consider. And then once you have that in action, you put that into your computational methods, in the sense of, let's say, you can put it in an Excel form or MATLAB or whatever possible software that you can use, then you can find your feasible solution. The most important part is how are you going to do it. Okay, the theoretical fundamental must be there, okay, for you to get that in action. Okay, so these are the example. Okay, the feasible solution meaning that if let's say, okay, we have this simple problem. If let's say I have x1 y1, does my x1 and y1 satisfy these problems? Okay, so you can see over here, if you put x 1 and y1 inside this equation, okay, if you put this inside your 5x and also, oh sorry, your 5x and also your 8y, you put that, you get 5 plus 8 equals to 13, which is less than 24. Okay, so it's still follow this particular inequality. So this one is feasible. Okay, so this one is a correct statement. All right. So whatever happened if let's say I have x1 and my y now is equal to 3. So in this case, let's say you check, it's like a check and balance situation. All right. So if let's say your x is 1, your 5 now multiply with 1. So you have 5 plus 24. So in this case, you already have 24 plus 5. Okay, 29. Okay, I'm sorry. So 29, does 29 less than 24? No, right? So it is not inside this particular boundary or constraint. So that's what we call x equal 1 and y equals 3 is infeasible. Okay, so what is the optimal solution? All right, optimal solutions meaning that once you have all the feasible solutions here, okay, all your feasible solution, and then from all these feasible solutions you get the best of all your feasible solutions. That is, once you have the best solution, that's what we call an optimal solutions. That's why I said sometimes it is not in the sense of maximum boundary or constraint or something like that. Okay. So you do the calculation, and then once you get the value from this particular example, then you identify in this example you have x equal to 4.8 and y equals to 0 as your optimal solutions for this problem. So later I'm going to show you how we're going to do it step by step. Okay, the concept behind finding this type of solutions. All right. But before we proceed to the example, okay, I'm going to highlight a little bit important terms that you need to understand. Okay, the first one is your variables. Okay, in this case of linear programming, you call your variables as decision variables. Okay, in this case you have s and also y. Okay, meaning that what are the variables that you can control or you can tweaks. Okay, so that is the decision variables. And then the most important part in your LP model formulation is the objective function. This one is very critical. Okay, sometimes we don't know what is it that we want out of the problems that we have. Okay, so that's why sometimes you want to have the best output. So how you can get the best output, or sometimes you want to increase your profit. You want to know how much you can get in one particular month, for example. Okay, so your objective function is different compared to the different problem that you have. Okay, that one is the maximum. Sometimes you want to know what type of cost that you can tweak, for example, to reduce your cost. Okay, so that one will be a completely different objective functions. Okay, so it must be according to what you want. All right. So, and then the last one is the constraint. Constraint is a limitation. So, as I mentioned earlier, it is not fixed to certain particular valuation. All right. It has sometimes certain complicated problems have many different kind of constraint. Okay, so it's a little bit tricky to identify which one is actually effect in your particular system too. Okay, so That is what we're going to look at later, right? So it's easy for us to discuss this in example term. Okay, so the first example I'm going to show you, this one I'm going to show a very in detail, and the next example I'm going to show just so that you have earlier um, earlier push for you to solve this that kind of problem. Okay, so the first one, let's say we have this problem. Okay, we have a certain valuation over here. Okay, this company produces wrenches and pliers. Okay, and then you can see it has three different columns altogether. Okay, the idea is that um, is in the valuation of, for example, the most important part is the contribution part. All right, so this is what we want. Okay, you can have a look a little bit about the idea behind this. Okay, but what we want is this. Okay, all right, what we want is, oh sorry, what we want is this. Okay, assuming we have point 0.4 ringgit, okay, or dollar, okay, for wrenches, the valuation for your wrenches, and also for the pliers is point 0.3. Okay, and then on the last column, okay, the available, okay, this one, this is the limitation. Okay, I'm going to change this particular example into a linear programming problems. Okay, so our intention is to solve this kind of programming. All right, so all right, we want to determine the number of wrenches and pliers to produce. Um, we want to produce, okay, the wrenches and pliers given the available raw materials, machine hours, and also our demand. Okay, so these are all the constraints that we need to consider. Okay, so the first constraint and the second constraint, the third constraint, and we have the demand of the limit. All right, the demand limit, meaning that we cannot exceed a certain limit to produce these particular wrenches and pliers. It may be because of your factory cannot cope with more than this particular materials and so on. Okay, there are lots of different constraints available. Okay, so if you notice at the bottom part of it, I put all of the slides, I put this yellowish color, okay, so that we keep on referring back to our original problem just now. Okay, uh, oh, by the way, you can always find how people get problems sometimes in the statement like sentences. Okay, especially in a long problems, and you can always simplify a long problem, that long problem, into a table, okay, for you to identify earlier. In this case, I put in the table already because I just want to focus on the solution of these particular problems. All right, so first things first, we first highlight what is our decision variables. Okay, so in this case, our decision variables is just two things: the wrenches and also the pliers. Okay, so we put P as a pliers and we put W as a wrenches. Okay, you can put any other values. It's not it's not limited to particular alphabets. All right, so okay, sorry, I forgot to. Oh, sorry, I forgot to uh, l- uh, cancel the animation. All right. So, the first step, to formulate this problem. Okay. We determine the decision variables W and also P. Now we this one is the most important part. We determine what is actually our objective function. So in this case, our objective function, okay, we utilize the contribution dollar per item in this part. Okay, as I mentioned earlier, okay, over here, and then we try to see the maximum profit that we can get by following this particular problem. Okay, so in this case, you put zero point 0.4 W for inches and zero point 0.3 S in the table for your P. Okay, later, how can we determine the constraint? Okay, I put all together first. Oh, sorry. Okay. So these are the constraints. Okay. You look back at all of your valuation on the table there. Okay. You have the constraint for your steel, for your molding machine, for your assembly, your demand, and also your demand for range, and also your demand for your pliers. Okay. So these are the constraints that you have. Okay. All right. Actually, there are also one other constraint that you can put. For example, like this one, W zero and P must be greater than zero, right? Because as I mentioned earlier, it's a unit of a thing. It cannot be less than zero. But in this case, if you notice, we put together because we already have the demand, the maximum, the ceiling demand for your range, and also the ceiling demand for your pliers. So you just put zero and zero over here. It fits. It include this one inside this also. Okay, so it does not matter. We try to minimize the constraint as possible. Okay, minimize does not mean that you can leave out the constraint. Okay, minimize meaning that if let's say you are able to improvise your problems formulation into a simpler value, that you can do, but you can never skip all your constraints. All right, but simplify, yes, but skip, no. Cannot. Okay, so now, okay. All right, okay. So now, how are we going to formulate in a mathematical ways and simplify this thing? All right. So look at this one. This is just similar as your previous example. It's just that it now has a little bit uh, easier for you to see in a different type of line. Okay, what I mean about line, I want to find the feasible area, okay, for my problem. So how to find feasible area, I want to see what are the lines involved in my graph. All right, so this is the thing. If you get confused, you can go back to your page 7 and make the comparison. All right, okay. Okay, all right. Okay, so here, okay, if you look at this one, what's the difference between page 9 and also page 8? Okay, you can see here. Okay, your maximum profit now becomes 400 for ranches and 300 for your pliers. Okay, why we do this? Okay, so why we do this? One of the main intention is, as I said earlier, we want to simplify as best as we can. All right, so in this case, you can see over here, if let's say I upgrade or I try to make this not in a fraction or not in a decimal place anymore, okay, and I tweak a little bit on the area over here, the valuation is just the same, isn't it? Okay, because this one, you forget about the thousand over here, but then you translate your thousand over into your objective function. Okay, it does not change anything, right? Okay, that is what we do. Okay, the idea, because we want to translate our mathematical formulation into a graph. Okay, so if let's say you have a graph which is point something, very small value, and the other one you have um 100,000 or 10,000 or something like that, so it's not nice, right? So it's just because of that. Okay, so now we proceed into the most important part. How can we graph our feasible regions? All right. So you can see. Okay, so you can see this one first. Okay. Oh, sorry. Okay, so we can see this one first. Uh, First things first, our idea is we want to see the feasible region. Where is the feasible region? Region. Okay, so we try to change that into a linear system. Sorry, a linear function, which during this linear function, you utilize your concept of a linear function and you utilize the concept of inequality, meaning that if you have a linear function and then you know that your linear function is less than some value. So meaning that your bounded region, your region is at the lower part of your linear function, right? And then if it is greater, then it is another way around, the counterparts of it. Okay, so you remember back your inequality problems. Okay, so what we should do first, okay, we graph the constraint one by one. Okay, first we graph the first constraint. All right, this is your first constraint. All right, this is just a linear function only. Okay, just plot in certain value, just put in, and then you get the value. Okay, this the yellow part. This is what we call all the regions. Okay, that is used by this particular linear function. Okay, that one is clear. One thing you have to notice, why this linear, okay, why this one, okay, for example like this one, why this is not a yellow anymore. Okay, because this one is a function as well, right? So by right, it should have also the similar regions over here. The yellow must be all inside here. Why it is not so in this case? Okay, so this one you look back to your original information whereby your things, okay, must not be negative. Okay, so you know that your W is just your ranges, and then your P is just your pliers. So all your information now you just focus on your uh, uh, quadrant, the first quadrant. Okay, the plus plus quadrant. Okay, that's why your yellow is just over here. Okay, the bounded region is just over there. Okay, and then later, all right, this is the next constraint. Okay, that's why I put the one at the box over here. Okay, now it's a little bit changed already, right? Now it's just becoming 12 and 15, but I think you get the point now. Okay, so the second one is for molding machines. All right, so you have W plus P must be less than 12. Okay, so this is your W plus P less than 12. Okay, the same thing happens. And then the blue line is for your W plus P less than 12. Okay, whatever happened over here, okay, this particular area, okay, why it is not bluish now? Okay, because now you have to consider the one in a yellow line. Okay, the yellow bounded region does not include this one. Okay, so if it does not include this one, even though your second constraint have this particular value, you only need to consider the one that is overlap between two different functions. All right, so I think you get it now. All right, so that's why your bounded regions is only this. Okay, and then we proceed again to the third constraint. This is your third constraint. Okay, what happened to this third constraint? Okay, you look at this third constraint. Okay, it reduce a little bit more of this already bounded region that we have. Okay, now it becoming a little bit smaller than the previous two bounded regions. Okay, so in this case you have this, and then now you can see what is this? W plus P less than 12. Okay, earlier it mentioned what happened to the constraint. Now in this case, your constraint over here, okay, give me some time. This one, right? Your earlier constraint, okay. If you notice, you don't need that anymore, isn't it? Because it just focus on your first constraint here, and it focus on the next constraint. Okay, this one, the constraint of W plus P is just included in your next one, so it does not uh, even though you have that, you just make it a little bit messy, but it does not help you in finding the constraint anymore. Okay, so that's what we call a redundant constraint. Okay, it is unnecessary. All right, so it is unnecessary. Once you find the unnecessary constraint in your case, you can just simply eliminate. Okay, now you can eliminate your constraint, but you can only eliminate the constraint once you really confident that this constraint is not does not give any benefit for you anymore. Okay, because it has no effect on the feasible regions. All right, so that's the only time where you can when you can eliminate this. If not, just fix it as it is. All right, okay, so now this is just another constraint that you need to consider. These two demand limit, okay, the ceiling of your production limit. Okay, you put the first W less than 8, and then your pliers less than 10. Okay, that's why you have two different horizontal and vertical lines over there. Okay, now what to do next? Okay, so this is your origin. This is your finalized feasible regions. Okay, feasible region. Feasible region meaning that all the value over here. Where is it? Okay, here. Okay, for example, you have a value over here. This one is inside your feasible region. If let's say you have value over here, also inside feasible region, your value over here, this one infeasible value, this one also infeasible value. All right, so that one is clear. So this is how we find so this is how we find the solution. All right, so go back to our initial problem. Okay, we want to maximize our Z. Okay, so our objective function is 400W plus 300. Okay, P. Let's say we put Z. Okay, Z is just our objective function. Okay, so we need to find our Z, which is just equal to 400W plus 300 P. Okay, so how to do just that? Okay, all right, sorry. Okay, this one. Okay, this. Okay, okay. I show you this one. This line. Okay, this line we call what we call this line? Level curves. Okay, this one we call a level curve. All right. Okay, this one we call a level curve. Okay, first things first, how can we find the level curve? Okay, level curve, actually, uh, as a start, you just try an error. Okay, you try to fix your z as just a constant. Okay, z as just your constant. Okay, and then that's why, for example, you put z equals to 1200. All right. So once you put z equals to 1200, okay, now your function is just becoming this, right? 300p equals to 1200. Okay. So this is just a linear function, isn't it? So this is just like a p equal to negative 400 over 300 p w plus 1200. Okay, so you can now do this line. Okay, this line is just a reflection of this. Okay, this is not necessarily you have to put 1200. This is just an example. You can choose any numbers whatsoever, but try to make sure that your line should have something which is inside the feasible region. If not, it does not make sense, right? Because if you put your line, your Z line over here, then how are you going to make the comparison, all right, and how you're going to find the best feasible solution in this case, all right? So now once you fix your first z, equal to 1200 just now, and then you see, is there a feasible solution if you increase your z? Because you know your first z equal to 1200, you have the first line over there, and then when you increase your z equals to 2400, see your line now getting into this side. Okay, so this is the idea. The idea is that this level curve, you it's like if you have a ruler with you, your ruler, you increase your ruler at the same slope. Okay, make sure the slope is the correct slope, meaning that um, if your slope over here is in that case negative, okay, wait a while, negative 4 over 3 actually. Okay, so this one also the same. Your slope is the same, negative 4 over 3. The difference is just on the location wise of it. Okay, it's like a ruler. You increase your ruler on the top. Why you go this side? Okay, why you go on over here? Because you know that your feasible solution must be somewhere around here, right? Here meaning that, of course, you want to find the values of W, which is the most, because we are talking about maximizing your objective function. So of course you want to find the value that is bigger, okay, larger. Okay, so that's why you move your valuation of your W to your right hand side and your P to the vertical top. Okay, so that's the idea. Okay, and then it give another valuation. What have ever happened if your Z now becomes 36,000, 3600? Okay, so you can see over here. And then once you move slowly further up until this particular valuation, you can see now your level curve will go or will meet to the most what we call this, the most part of your 1 2 3 4. Okay, the most part of your 1 2 3 4 5, the most part of your pentagon, in this case 1 2 3 4 5. Okay, pentagon side. Okay, so this is your valuation here. Okay, so this is actually your optimal solution. Interesting, isn't it? Okay. So we settle on the part of finding the optimal solution there. Okay. The next question. Okay, once we find, we know that this particular vertex, not a vertex, this particular intersection is the optimal solution. How to find the value of my W and the value of my P? Okay, that is the question. All right. Because once we find the value of my P and my W, then only I can find the value for my Z. Okay, Z is my objective functions. Okay, now, okay, now we go back to our linear algebra earlier. Okay, you have two intersection line. Okay, this is your intersection line 1 and this is your intersection line 2, and you know if your linear line intersect with each other, you know the intersection line, you can get your P and Q, right? It's just by solving sorry, it's just by solving two linear function together, right? Simultaneous equation, correct? That is what we're going to do. Okay, so this is what you have. You maximize your Z. Your constraint now, you only need to consider two different constraints together. This is your first line. Yeah, this is my first line and this is my second line, and you know this is just a linear function. Okay, so just forget about the inequality part over here. Okay, so you know this is just okay, this is what we call a binding constraint. All right, not that important. Okay, so now this is how we're going to solve it. This is just solving your uh, simultaneous simultaneous equation. Okay, you're trying to solve this equation. This is your first line just now, and this is your second line just now. You can do it, right? Okay, because this is just a simple solution. All right, you can also use your calculator, doesn't matter. Okay, as long as once you have two different linear line, Okay, or linear function, and then you can solve for your W and also for your P. It's just a straightforward valuation. So based from here, you know that your W now is 50. Okay, where is it? And your P now is 50. Your W is 50 over 7, and your P is 30 over 7. So in this case, this is what we call optimal variable. Optimal variables. Okay, optimal variable that will give your optimal solution. Okay, so your optimal solution now is your Z. So Z is what? Z is just your value over here. Just put your value W and also P, your optimal variable there, and you get your maximum solution. So your value of your Z now becomes 4142, 6 over 7. Okay, done. Clear. Okay, so this is just the summary for finding it. Oh, sorry, for finding it. Uh, it is actually a corner point, but which corner point is the feasible region? That is the question. All right. So how to get the corner point? You need to utilize your idea of level curve just now. Okay, your Z as a level curve. And then the rest is just follows according to the graph. What is binding solution? The binding of your linear line, it binds together, and then you get the constraint that you want, the solution that you want. And then what else? uh, there is always an optimal solution. All right, there is always an optimal solution, even though for a simple question like this one. Okay, more than one solution may be optimal in some situation. Okay, in this case, we are going to look at other different kind of examples. Okay, whereby sometimes your level curve move forward, and then suddenly your final solution is actually in the a value, for example a horizontal line or a vertical line, in which case that one you have more than one solutions. All right, so I hope you get the whole concept of this particular ways of how we solve the optimization problems by using linear programming. Okay, so this is the example that I want you to try. Okay, I'm going to give you a bit of a idea about the question there, and then I give you the final solutions, and then I want you to work out, okay, how you can get to the final solution based on the previous example that I've given earlier. Okay, so if let's say this guy wants to carve wooden soldiers and trains. Okay, this is just a toys. Okay, and then all these particular values over there, each soldier build blah blah blah, each train build blah blah blah. Okay, these are the thing that you need to transform or transfer into a table that I have earlier. Okay, this is the example of having a situation where it is in a statement form, but you need to realign, readjust into mathematical formulation. Okay, to me, the easiest part is first put it in a table form first, so that you know your variables is what, you know your constraint is what, and then it does not confuse. For example, like require 2 hour of finishing labor, what is that? Okay, so it is just if you put in a table form, you know that it's just your limiting valuation that does not require complicated information, right? This one is just similar to your demand in your previous problem earlier. Okay, so the same thing over here, and then these are all the constraints given. Okay, and then our objective function is we want to maximize the weekly profit. Okay, and then these are the decision variable that you have. X1 is for your soldier wood, and then your X2 is your train wood. Okay, and then how you're going to find your optimal solutions there. All right, so these are the solutions. Okay, how you're going to transform your solution into this? Okay, wait. Okay, this is the final version that I want you to construct. Okay, you can do this exactly as the way I do it in the previous example. Okay, it's just that your objective line now becomes the name there. Okay, and then the yellow in color is your feasible solutions, and then your z over here, z it start with z equal to 60 right now. This one is your level curve right now, and then this one, your level curve heighten up until over here where you have your g equals to g becomes your optimal solutions over here. Okay, this is your level curve for your final solutions. Okay, like this one. Okay, so this is your binding. Okay, this is your binding, what we call that, a binding equation. Okay, so this one is sorry, binding constraint. This one is your first binding constraint, and this one is your second binding constraint, and then from here you can get this solution for your optimal solution, or optimal variable by just simultaneously solve your two different linear equations together, and then you will get your optimal variables, and then once you get the optimal variables you are able to get your optimal solutions for your z. Okay, so I hope you get the knowledge over here right now. I hope you enjoy the video, and I hope you are able to construct your own linear programming problems and solve it accordingly. All right, so I'll see you in the next lesson.